Okay, so now let's have a look at one example. Example 7. It says sketch the graph of y equals x to the 4 minus 4x cubed, stating the coordinates of all axes, intercepts, any stationary points, the nature and any points of inflection, and then state the values of x where the function is decreasing and concave up. So we've got our original function y equals x to the 4 minus 4x cubed. So it's just our basic polynomial, a quartic polynomial. To sketch, to look for stationary points, we need y dash, the first derivative or the gradient. So let's differentiate that. So differentiating our normal polynomials, we get 4x cubed minus 12x squared. Because we need to consider the nature of the stationary points and any inflection points, we need to look at the second derivative, or y dash dash. So differentiating our y dash, we get 12x squared minus 24x. So we're going to go through our 6-step process. So step 1, find your intercepts. So x int when y equals 0. Okay, so or back to your original function, your y equals or 0 equals x to the 4 minus 4x cubed. Let's factorize x cubed out, so we get x minus 4 left over. So using null factor law, we get x cubed equals 0, or x minus 4 equals 0. So therefore x equals 0 because the cube root of 0 is 0, or x equals 4. So we have x intercepts at 0, 0 and 4, 0. Step 2, let's work out the y-intercepts. So y-int when x equals 0. So back at your original function, y equals 0 to the 4 minus 4 times 0 cubed, which is 0. So therefore y-int at 0, 0. Step 3, let's work out the stationary points. So stationary points when y dash equals 0, so that's your gradients equals 0. So going back to your gradient function, so y dash equals 4x cubed minus 12x squared. So 0 equals 4x cubed minus 12x squared. Let's factorize. So I can factorize out a 4x squared out. So I'm left with x minus 3. So using null factor law, so 4x squared equals 0, or x minus 3 equals 0. If 4x squared equals 0, then x is equal to 0, or x equals to 3. So we've got two possible stationary points, when x equals 0 and when x equals 3. We need to check the nature using y dash dash. So we need to check nature using my double derivative. So when x equals 0, my double derivative, so what was it? 12x squared minus 24x is equal to 12 times 0 squared minus 24 times 0, which is 0. So remember back on the table over here. So if our first derivative is 0, so it's either a sad face, happy face, or a stationary point of inflection. But right now I've worked out that my double derivative is 0. So it could possibly be a stationary point of inflection. So the only thing we need to check as well is the changing of signs of our double derivatives, just to make sure that it is a point of inflection. So back over here, so y dash dash is 0, so therefore it's a possible point of inflection. So let's check concavity on either side, because if it's a point of inflection, it needs to have a change of signs on either side. Check concavity on either side. So we need to draw up a little table. We're checking x values versus y dash dash values. Not y values, not y dash values, but double derivative values. So my point of interest right now is when x equals 0. So pick a little bit to the left, so negative 0.1, and pick a little bit to the right, so positive 0.1. Substitute your y dash dash values in, so 12 times 0.1 squared minus 24 times 0.1 gives me, let me quickly do that on the calculator, 12 times 0.1 squared minus 24 times 0.1 gives me negative 2.28, so it's negative, whereas over here we have 12 times negative 0.1 squared minus 24 times negative 0.1, which gives me minus 24, 2.52, which is positive. So that's good because my y dash dash has changed signs on either side, which means that we do have a point of inflection. So therefore, y dash dash has changed signs from concave up, because it's positive, to concave down. So therefore, well, we know when x equals 0, y equals 0, because that was one of our x-intercepts and the y-intercepts, so we don't need to go and recalculate the y value. So therefore, we know that at 0, 0 is a horizontal or stationary. So it's a horizontal stationary point of inflection. And in fact, we know it's going to be of the shape of, it's going to go concave up, so kind of like a smiley face, and then it's going to go concave down, so like a sad face. So we know it's going to go like in that shape there. So that's our first stationary point when x equals 0. So we know it's a stationary point of inflection that looks like this shape here, because it goes from concave up, so half a smiley face, to a concave down, half a sad face. We now need to work out what the nature is of the other stationary point when x equals 3. So let me just draw a border so I can have a bit more space. There we go. Okay. So we're still at point number 3, working at the stationary points. We're still checking the nature. So when x equals 3, checking the nature using the double derivative. So it was 12 times 3 squared minus 24 times 3, which gives us 36. And 36 is positive. So therefore, if it's a, so back to the table, whoops, too much. So we know that when x equals 3, the first derivative equals 0. So it's one of these top 3. And we now know the double derivative is positive. So it's happy. So it's minimal worry. So it's a happy face. So it's a minimum turning point when x equals 3. Or in other words, a concave up. So therefore, whoops. I mean, you can either write concave up or minimum turning point, same thing. So concave up, smiley face, or you can write minimum. So we need to work out the corresponding y value for when x equals 3, because when we graph something, we need the xy point. So y value when x equals 3 is 3 to the 4 minus 4 times 3 cubed, which gives us negative 27. I'm pretty sure. Let me just triple check that in the calculator. 3 to the 4 minus 4 times 3 cubed does gives us negative 27. So we can conclude that therefore 3 comma negative 27 is a local minimum stationary point or turning point. Okay. So what do we know so far? We've worked out so far that we have an x-intercept at 0, 0, and 4, 0. At that point 0, 0, it's also the y-intercept. We've worked out that there are 2 stationary points. That's when your gradient is 0, your gradient's flat. Number 1, at 0, 0, you have a horizontal point of inflection because it goes from concave up to concave down. So half a happy turning into half a sad face. And then we also know that at 3, negative 7, it's going to be a smiley face because your double derivative is positive. So that's a concave up or a minimum. So that was step 3. The next step we need to look for is solving for any point of inflections. So back in the table, what's the property of a point of inflection? So the key point of a point of inflection is, for starters, your second derivative is 0, and you have signs changing on either side. It's pretty much what we did last lesson. So step 4, let's point of inflection. So point of inflection when y dash dash equals 0, and you have concavity, or your y dash dash changes either side. So the sign of y dash dash changes left and right. So we need to solve for y dash dash equals 0. So we're solving for 0 equals 12x squared minus 24x. I'm going to factorize it out. So 12x, I'm left with x minus 2. So using null factor law, we have 12x equals 0 or x minus 2 equals 0. So x equals 0 or x equals 2 are our 2 points of inflection. Now we have already considered x equals 0 because all the way down here, if we worked out at 0, 0, it's a horizontal or stationary point of inflection. All good, we know that. So all we need to consider is when x equals 2. What is it even a point of inflection? Because does the concavity change either side? And if so, what does it look like? So let's consider when x equals 2. Let's do our concavity check. So that means we need to draw our little table up. And we're checking your y dash dash values. So x versus y dash dash concavity check is using the second derivative. So the point of interest is when x equals 2. Now a little bit left, a little bit right. So 1.9 and 2.1 is a little bit left and a little bit right. I'm substituting 1.9 into the y dash dash. So it's 12 times 1.9 squared minus 24 times 1.9. So that gives us 12 times 1.9 squared minus 24 times 1.9 gives me negative 2.28, so that's less than 0. Obviously at the point 2, y dash dash is 0 because that's the point of inflection, theoretically. And then 2.1, so 12 times 2.1 squared minus 24 times 2.1 gives me 2.1 squared minus 24 times 2.1, 2.52. So that's positive. So that's good. My concavity has changed on either side. So therefore, concavity has changed on or either side of x equals 2. So we know it's a point of inflection. Again, if we want to sketch something, we need the y value as well. So the y value at 2, so that's 2 to the 4 minus 4 times 2 cubed gives us a negative 16. So therefore, point of inflection is 2, negative 16. And it's not a stationary point of inflection, so it won't look like a flat part of it, but we do know it goes from a negative concavity to a positive concavity, so it's going from a concave down to a concave up. So we know it's going to look like that, but we know that at that point of inflection it won't be flat. So that's another key point. So we know that a point of inflection is at 2, negative 16. So far we've got our x-end, we've got our y-end, we've got our two stationary points, one of which is a stationary point of inflection, the other one is a smiley face, it's a minimum. We've also worked out that there is also one more point of inflection at 2, negative 16, which goes from a concave down, because y dash dash is negative, to a concave up shape. So it's like half a sad face turning into a half a smiley face. Right, what's after this? We need to look at the domain and range. So are we given a specific domain to draw over? Well, if they don't give us a specific x values to draw over, it's assumed that our domain is all the reals then. So step 5, our domain is then all the reals, and because it's a polynomial function, there's no exceptions, so there's no bad points at which you can't divide by 0 or use square root of negative. So our y values, our range will also be the reals. Step 6 is to consider any long-term behaviors and or asymptotes. Asymptotes you kind of consider using domain and range anyway, when you consider are there any points at which you can't divide by 0 or you can't square root to negative either. So step 6, let's look at long-term behavior. So that's looking at, as x gets really, really small, what does your y value look like? Well, if my x value gets really, really small, so let's think about if something is negative and it's to the power of 4, I end up with a positive anyway. And I'm taking away from something which is smaller. And if this is a negative cubed would become negative, and then I'm subtracting a negative. Essentially, I'm adding as well. So I've got a positive number adding something else. So my answer will always be a positive number. So that tells us as x gets really big, my y value is going to be a positive value. And in fact, it's going to get really big as well because I've got powers of 4 and powers of 3. So we can say that as x gets really negative and big to the left, y gets positive and big as well. And then as x gets really big to the right, gets positive and big, well, a positive to the 4 is still a positive. A positive cubed is positive. But because x to the 4 is bigger than x cubed, this dominates, so you have a bigger number taking away a smaller number, so your answer will still be a positive value. And as x gets big, your y value answer is also going to get big because it's just high powers. So as x gets big, y also gets big, positive. Okay, so that brings us to, let's draw our graph. Okay, so label your axes, x, an arrow up, y. Let's look at the key points that we need to sketch. 0, 0, 4, 0, 3, negative 27, and 2, negative 16. So along the x's, I need to make sure I need to reach up to 4, because I've got the x-intercept at 4. And in terms of y values, I need to make sure I need to reach at least to negative 27. So I can draw that in. So let's make that 0, 1, 2, 3, 4, negative 1, 1, 2, 3. So negative 10, negative 20. And then negative 30, and then that would be 10 as well. 20. Okay, we've got a x-intercept at 0, 0, so mark it in. So we've got 0, 0. We've got x-intercept at 4, 0. So let's mark it in and label it. We've got y-intercept at 0, 0, so we've marked that in already. The stationary point of inflection is at that point, so we know that it's a flat point here and then goes down-ish. At 0, 0, we've got the other stationary point, the happy face, at 3, negative 27. So 3 across, negative 27 is about here. So mark that in. So 3, comma, negative 27. I've also got the other point, 2, negative 16. So 2, negative 16 is about here. So 2, whoops, negative 16. Now let's do our best to join the curves. All right, what do we know? So we know that 3, negative 27 is a smiley face. So we know it's going to go up like that. And it's going to cross link up to the x-intercept there, and it's going to go up forever. We know that at 2, negative 16, it's a point of inflection that goes from a concave down, a sad face, to a happy face, a concave up. And this is where the happy face is, because that's the remnant of the happy face. So we know that there is a, it's going to join up there. Like that. And then we know that at 0, 0, it's a point of inflection that goes from a concave up, so a half a happy face, and then turns to a half a sad face. And this half a sad face is what going to connects up to the other sad face or concave down part of the point of inflection at 2, negative 16. So let me just draw that back, draw that better again. So we know that's a concave down, it's going to meet back there. And then over on the left of that point of inflection, we know it's a concave up kind of shape. Like that. So there we go, we've drawn our graph. We've labeled the key points, our x-ins, y-ins, stationary points, and point of inflection. Let's label our curve. So this is y equals x to the 4 minus 4x cubed. We've stated the domain and range already. So domain is all the reals. Our range is all the reals as well. That's pretty much it for part 1. So you can see that one of these is a complex question, not because it's hard to do, because it's pretty much the same steps like again and again, but it's just it takes a long time to get one of these done. So you always go for x and y and stationary points when your first derivative is 0. Then you check your nature using your double dash, which may also include a concavity check if you get a point of inflection. And then you work out the corresponding y points, obviously, so you can plot it. Then you check the point of inflections when your double derivative is 0, and then you check concavity. Then you look at your domain and range. Are there any values which your graph cannot take, or are there any asymptotes? Then you look at the long-term behavior as you go really left and really right. What happens to the y values? Is it pointing up or is it pointing down, positive or negative? So now let's tackle part B. So let me draw another margin because I think we need more space. Is that going to work? Yeah, there we go. Part B says state the values where the function is decreasing and concave up. So this is just purely using the definition. So B part 1, function is decreasing when y dash is less than 0. So that's the definition of decreasing. So this is going back to 2 lessons ago. So when your gradient is negative, that's when your function is decreasing. Well, look at your graph. From graph, where are your values for which your gradient is negative? So that happens when x is less than 0 or between 0 and 3. So essentially, all these values here, your gradient's going downwards, except for the point at x equals 0, because that's a stationary point. But anything over this side here, your gradient's negative. So for these x values, that's where your graph is decreasing. Because back over here on the right, your gradients are all positive, and that's an increasing function. So from graph, that happens when x is less than 0, but not equal to 0, because when x equals to 0, it is the stationary point, and that's when the gradient is equal to 0, not negative. Or when x is between 0 and 3. Not including 3, because 3 that's the stationary point. That's when your gradient is exactly equal to 0 and not less than 0. Now, part 2, when is the function concave up? Well, what's the definition? So function is concave up when your y dash dash is positive. So from A, you've got the point of inflection at 0, 0 and 2, negative 16. Points of inflection at 0, 0 and 2, negative 16. So from the graph, where is the concave up? Essentially, concave up is where it's like a happy face, right? So we know it's kind of a happy face over here when it's to the left of 0, so when x is less than 0. And we also know, well, this part here is a concave down, because when we did the concavity check here. And then this part here, we've got concave up as well, and it keeps going up there. So from the graph, concave up, function is concave up when x is less than 0 or when x is bigger than 0, because that's the other part of the smiley face that you've got there. And because of the concavity checks that we had when we were solving for the point of inflections. So if every time you are asked to sketch a graph, if you can follow the 1, 2, 3, 4, 5, 6 steps and make sure you have a nice and pretty labeled graph, then you're good to go.